Hello to all. This presentation under the data center facility and modular data center track is the power distribution challenge for the 1 megawatt IT row. Yes, 10 100 kilowatt racks in a row. Can we power them? And if we can, how will we do it? I am Gabi Mendreci, Positronics Innovation Team Captain and Director of Sales in Europe. And we have here with us today
Sean Halpin, Director of Engineering with Dataplex Group.
And Jim Weinheimer, Director of Customer Solutions for Virtual Power Systems.
All right, welcome and good morning, good afternoon to all who participate and they're watching our presentation. In order to frame the discussion, with the advent of artificial intelligence and increasing demand of cloud computing and cloud storage services, data center power usage is growing at unprecedented rates. And increasingly, racks with higher power densities will dominate the white space. And while a lot of attention is given to advanced cooling solutions needed to sustain compliant operating conditions, is it time to start giving the same level of attention to the increasing demand for power? So the real question is, what could the future of power infrastructure look like? And with a vision of having 10 100 kilowatt racks, this discussion is an exploration on ways to distribute 1 megawatt of power, 1 cool megawatt of power for 10 racks. Wow. And in this presentation, the following points will be addressed. We'll have a 1 megawatt solution utilizing existing three-phase AC power distribution methods. That is Sean's presentation. We will look at benefits of virtual power management. And at last, we will have a look at a new vision approach with a smart power distribution system that comes from the aerospace sector, utilizing a cool 1 kilovolt DC power distribution architecture. And with that said, I will let Sean take over. And Sean, you have 5 minutes for your presentation.
That's great. Thank you. Thank you very much, Gabi. So this is a basic layout of the infrastructure for an AC system for a data center. It's not resilient. We're not focusing on that necessarily at the moment. It's just a straight through from your power station, your utility, all the way through to your rack. Some of the main components are your medium voltage switchgear, your transformer, bringing it down to whatever voltage you're looking for in your 400 volt three-phase, into your primary switchgear. Your primary switchgear then separating off to your air handling or your mechanical loads and into your UPS or other supporting equipment, then on into your secondary switchgear, which then subdivides out onto into your IT load. So if you want to flick on there, Gabi. We are more this standard infrastructure. I don't see changing too much if we're going to go to a 1 megawatt rack. Where I see the biggest changes are sort of from your secondary switchgear on. So in this case, this is realistically we have two main options to us that haven't changed. One is to go with overhead bus bar, albeit it would not be the same type of bus bar that generally we use at the moment in a data center. Now, that's not to say there are some high amperage options available to us, but in my mind, I would see this as being sort of an encapsulated bus bar. And similar to a rising bus bar system that you'd have in, say, a hotel or a hospital or something like that, with very large tap-offs. And then if you want to flick on to the next one, Gabi. The second option to us again is the standard whip, where you would be feeding 160 to 250 amp MCCBs out onto your rack with a standard, Hofer cable or something similar to that. But realistically, the biggest challenge is actually the interface between the infrastructure and the rack, which is where Gabi is going there now. And that's kind of where we're limited at the moment. Realistically, there are only a couple of, commercially viable plug-in style connectors. We could go with perhaps, and there are, these are mostly European centric, but there are UL versions of these as well for the US and other Asian markets. But typically, we could look at the standard cam lock that's used already for generator testing and high amperage loads and connections. There's a Mennekes style, the HASP style, that's available, the silver one there, yeah. And then there's the Marshall version, and these are all, so your standard IEC connector is usually about, you know, you're going up to about 125 amps ish, and anything then above that, you're starting to move into more marine and aeronautical connectors, certainly at AC. But the main thing we need to concentrate on here is the fault current as well. You know, typically your standard MCV or whatever up to a point is anywhere between 10,000 to 16,000 amps. You don't want it to go really above 10,000 amps at the rack. So that is a challenge in of itself now with the increased load. And the way I see kind of getting around it, keeping an eye on my time, is if you flick on to the next one, Gabby, please. How would we overcome it without changing too much with our infrastructure? I think it might be hanging. There you go. And this is just a very quick mock-up. You know, in my mind, how would you have a 100 kilowatt rack? If someone were to come to me today and say, I have a requirement for 100 kilowatt load, in my mind, when we were first thinking about this, I was thinking you could have two 50 kilowatt, you know, on chip or liquid cooled racks. You would have your overhead encapsulated busbar or high amperage busbar, then feed down into almost like a mini RPP that would sit beside the racks. You can have, you know, a single feed, you know, feeding into the BBUs in an OCP rack, or you could have an A and a B feed, have one either side or two in the center, or whatever way you want to approach it. But it's more of just a concept. You know, the key thing here is that you're breaking down the fault protection, because while you're coming in at 200 or, you know, 160 to 250 amps overhead with, say, a Menica's connection, on the back of it you would have your standard IEC connectors. And then the next stage, I suppose, which are all subdivided off of their own MCBs. But realistically, I think the next step after this would be to actually start integrating the switchgear, the low voltage switchgear, with the compute load itself. And that is my part. So I'll hand it over to Jim now.
All right. I think I'll probably be more like 6 minutes. So thanks, and sorry for eating into your time, Gabby. So today, Sean and Gabby are here to tell you how a 1 megawatt row can feasibly be built, and all the details behind delivering extreme density. But I'll give you some examples to show you that you actually don't have to build a 1 megawatt row to actually get a 1 megawatt row. And if you're still set on building the whole megawatt, everything I'm about to tell you will apply just the same. And it's about making what you've built more efficient and unlocking all the power capacity of the physical infrastructure to do the real work. Now, some companies have full control across their stack, and they've honed the process of providing real-world load specs to the facilities teams, but those companies are the exception. By and large, it's still an imperfect art to closely match the IT and the electrical system capacities. So let's assume for the worst case scenario that the difference in percentage between the idle power load and the max power load is the same for your 10 kilowatt racks as it is for the 100 kilowatt racks in the 1 megawatt row. If we apply the same deratings to the 1 megawatt row as most of us have experienced in data center facilities planning, the actual draw of a 1 megawatt row will be somewhere in the 700 kilowatt range. And that uncertainty about the real world loads leads us to overbuild the electrical systems and to strand capacity, which means we're building for the worst case and not the average loads. There's many good reasons that we're doing that, but we can get closer by using software-defined power. On the next slide, you'll see the typical case where the actual loads are lower than the design specs. The infrastructure for a 1 megawatt row is going to be expensive, and you want to be able to use all the capacity that you've purchased. And to do that, maybe you add more equipment to this distribution system, or maybe your developers find a way to serve more requests on the same hardware for cat pictures or whichever social media post about which island you're going to vacation on for your birthday. But whatever it is, you're able to drive that load up on the hardware and get much closer to the capacity of the electrical system, as we can see on the next slide. So even though you're now using the hardware more efficiently and your actual draw is equal to the hardware specs, there's still a small buffer just in case. On the next slide, you'll see we're now monitoring the system's power draw, and we've added an energy storage system in the form of batteries that can supply some of the power to the IT load when it's needed. The energy storage systems here replace the buffers that are usually reserved on the physical infrastructure that allows all the capacity of the purchased electrical system to be used. In most cases, when we make this change, the peak load can be driven up to the limits of the physical infrastructure, and any power above that's provided by the energy storage system. So for this example, we've recovered 10% of the system's capacity, and now this 1 megawatt row truly has 1 megawatt of capacity for 1 megawatt of load. The energy storage systems on the market today are just one element of software-defined power, and they're available with multiple manufacturers with various chemistries, typically lithium-ion, but others are becoming increasingly popular, especially in data center environments where we're sensitive to the potential hazards of lithium, but the variety allows you to choose the best chemistry to suit your application. On the next slide, we're layering in more software to control the racks that you've added in to drive up that average load when the demand for cat pictures isn't so high. So when the demand on the primary systems is high and it's reaching the peak power draw, the energy storage systems can help to limit the load seen at the upstream systems. But eventually those energy storage systems will be depleted and the load will need to be shed to maintain the SLAs on that priority one equipment. The controlled devices here can be in-rack devices, smart circuit breakers, intelligent power shelves, or almost any other network connected device that's capable of limiting or switching load. And the important part is the control of these devices to maintain the high SLAs on the priority one equipment. The power control software here is also providing feedback to the software stacks running on these racks to be able to shift load in the cases where the primary racks are at peak draw and no additional capacity is left for the priority two racks consistently enough to keep them online. And software here is consistently monitoring the state of charge and the state of health on the energy storage systems, the load on the electrical systems and the individual racks, and it's comparing all that against the electrical system capacity to make changes to the policies that decide where power is routed. So the software monitoring and the control paired with those hardware devices creates the ability to dynamically or programmatically control the systems to pull the typically unusable capacity for other racks. We've only touched on two examples here, but we're able to more efficiently use this 1 megawatt. And there are many other software-defined applications using some of the same elements that we can use to unlock more capacity. So one of those is redundant power, and I'll talk more about that later. But if you're interested in learning more, please reach out. We'll be happy to talk more about them. But my time's over. On to Gabby.
Well, we're all limited within the spectrum of the presentation time because we do have the questions portion at the end of the presentation. I'm going to start the timer on mine as well. So here's an advanced concept. This is a concept of a power distribution system utilizing an advanced, I'd say, objective of putting 1000 volts DC between the rectifier section into the actual racks. Now, considering for a row of 10 racks, if we want to feed 1000 volts DC to the rack, we basically need to make provisions for 1000 amps. And the reason this rectifier switchgear is placed in the center of the row is because this will simplify the bus distribution on each side with 500 amps going in each side. So 500 amps going in this portion, 400 in this portion, 300, 200, 100 to the last rack. And this is achievable with an overhead bus system, such as this one shown in this configuration. And this overhead bus is a smart, holistic type system that could also be replaced with a whip wire configuration, just like what we used to. But again, the key part of the functionality in such a distribution system is to use a smart and safe connector that has sensors built in, and also a smart and safe wire that has the ability to detect faults, to detect partial discharge, and react very quickly. In order for such system to react so quickly as needed, it's only feasible with solid state breakers. Conventional breakers simply cannot handle this type of fast reaction that's needed in a system as shown. So just let's look at this in a little bit more detail. And considering the standard rack size that's shown in this diagram has the ability to fit IT equipment, the IT gear here basically would require 100 kilowatts of power. So let's assume we have the gear that fits in the standard rack, obviously for the down conversion element, because taking 1000 volts DC and converting it down to 50 volts DC to go into the IT equipment, we need to do that. And it's a huge challenge. That is probably one of the main challenges as such an architecture. It can be done. And what we show in this concept is a section utilizing only a capacitor array bank and a section utilizing a mixture between a capacitor array bank and a battery bank. And the idea of down converting 1000 volts DC to 50 volts DC. So if we have 100 amps at 100 volts DC, the challenge really behind the rack will be to supply 5 bus links at 400 amps each, because that's a total of 2000 amps of 50 volt at 50 volt DC. It is a challenge, but these bus links would be standard. They can be configured to be plug and play at each level, whatever the level may be. 5 of them will be sufficient to distribute the power accordingly on the rear of the rack. With similar situation, when we're looking at the solid state breaker, and we were working on solid state breaker technology with companies such as Atom Power. This image is a courtesy of Atom Power, and they have pretty good advanced development with breaker points at around 100 amps. So it can be set objectively to trigger a disconnect at 110 amps, let's say, rather than a more larger spectrum with the conventional type breakers. But also on the backbone of this system, it's a monitoring system that's used for logic monitoring and reporting. This makes this whole system a holistic design from protection device all the way to the load. So you cannot just take any connect, you cannot take any cable and make it work. They have to work together, and the cable is designed to work with the connector together and so on. The logic and the monitoring and reporting system is able to detect partial discharge continuously. And as soon as partial discharge is detected, the system will know what to do, and that event would be communicated to the load and to the source simultaneously, and therefore redundancy can take place rather than anything. And the system is it's designed for ultra fast reaction. The actual reaction, it's 25 microseconds from the time an event is detected to the time where the breaker turns off and turns the system on for the redundant portion. But just to have a visualization about this, imagine you have an axe and you swing that axe at the cable, and the cable it's 1000 volts DC passing 100 amps continuously through it, and you swing the axe at it and you sever the cable. Well, the way the system is designed to work, by the time the leading edge of the axe passes 0.7 millimeter past the shield braid on the cable, the breaker turns off. So no matter how the deterioration occurs, it is designed to the human safety element is primordial, and it's just making the system operate with safety being first in place. It is well known that a distribution system for 1000 volts DC would have a day at the park with the UN qualification. And therefore it is important that we bring know-how from the aerospace industry into the data center for the future for the future designs. And I guess that's it. We want to move to the next slide, which talks a little bit about the benefits of an alternative system. Obviously, an alternative system would bring a potential cost reduction of infrastructure. If you think about reduced carbon footprint also, imagine the lowering the amount of copper needed to do all this power distribution, because in a data center in three-phase final distribution, we've got miles and miles and miles of cable with a lot of copper in it because carries a higher current. And just to manufacture those cables, to melt all that copper, to form all that copper, all the insulators and all that, it requires energy, and all that energy turns into the atmosphere in some form. Reducing this infrastructure will reduce significantly the carbon footprint from the startup cost. The increased power efficiency also, apparently ABB is reporting that with a DC power distribution system, they reduced losses by 70%. So in other words, imagine if you now have an efficiency in AC distribution at 80%, you increase, just by reduction of those losses, you increase that efficiency to 94%. That's the same correlation. The improvement in the power management options also, like this is unprecedented, because now you can sit at a terminal and you can control power allocation, power management, and like Jim presented from virtual power systems, you can allocate peak shaving, you can configure your power allocation. And in the end, the ultimate will be, with AI increasingly developing, the ultimate objective would be that each chip would predict how much power it needs over the next 5 minutes or over the next 5 seconds. It doesn't matter, but each chip will demand how much power it's going to need over the short duration of immediate future, and then the whole system can communicate this information and balance accordingly. And again, with the power factor impact, obviously DC power factor will allow to be optimized at the rectification stage, and phase balancing complexity is out of the equation, and a lot of benefits basically. Now, the highest I see benefit here is the improvement in human safety elements. We imagine elimination of arc flash, imagine elimination of issues that generally have a qualification agency type attention on them. And last but not least, interfacing UPS systems and interruptible power supplies can be easily integrated, because their batteries are, our concept involves batteries already. And also, if the facility is close to renewable generation, such as wind or solar, it'd be easy to bring the DC and synchronize it seamlessly without much of an effort like it is nowadays for AC. So, in a nutshell, that's what we had for you today. We hope it was interesting, and we do have a 20-minute section for questions. But before that, we have a call to action, and obviously, anybody wants to join this work group, please contact Mr. Mark Danzi, and our contact information is shown here for you to take notes, and just reach out to us with further questions or specific questions. Now, open discussion, the table's open. Any questions?
Hey, Gabby. Yeah, so Mark Danzi has actually posted a couple questions in the comment section. Mark, I know that you're still on the call. Do you want to just ask those verbally to Gabby?
How do I see the comments section?
Yeah, sure, no problem. It's in the session window on the right-hand side. So one of the things I was interested to know about really sort of the maintenance aspects for this type of high power design. Maintenance is one aspect, I think, to start with, and the other aspect is around the testing, the IST for this type of high power design. How would you recommend approaching the maintenance? And
basically thinking about is this question for the new concept of the 1 kilovolt DC distribution system?
I think it's interesting to apply this to both sort of the existing, sort of existing types of methodology that could be used, but also for a new style, if there's sort of pros and cons around sort of just thinking about the maintenance, which would be, what are the pros and cons of maintenance for this type of system, for example?
Well, so first of all, at rack level, the equation is very simple because on the rack side, you're still dealing with low voltage but higher amperage. So the caution required for current maintenance will apply equally to the rack side. And that is the part where usually you get a higher, the higher circulation is plugging a wire or changing something or whatsoever. But in terms of the power distribution system now, where you've got a capacitor array bank, obviously this is a system that needs to have its own cautionary procedure and the methodology required for maintaining. However, in such systems, the maintenance would be a lot more reduced. Should anything need to be changed, it would require a disconnection of the branch that needs to be changed, and it would it will require shorting of all capacitors for a safety element in order to be able to access and service physically the units. Obviously, new training, new methodology, and procedures would have to be written accordingly.
And that's probably one of the biggest challenges is training between your operations teams that would already be quite familiar with AC and the procedures they have in place for AC. Realistically, it would follow more similar procedures to to specialist plant like the UPSs and other equipment that typically deals with DC. What I would say is that certainly from maintenance, even from an AC perspective and from a DC perspective, the fault levels you're talking about is probably one of the biggest risks, along with charged capacitors. But your fault level is probably the biggest issue. Depending on your perspective, fault circuit, whatever the circuit is actually like, and whatever your transformer configuration is, you're talking about having maybe 18 plus thousand amps, certainly from an AC perspective at the rack. So you start working on the basis that the equipment essentially has to be maintained in the same fashion as you would start maintaining switchgear. Depending on where in the world you're from, that might, ideally it would come down to switching the equipment off. But if you had to do it in a live environment, you'd have to wear the full arc flash gear and that kind of thing. The big question really is, and I would say that it's not insurmountable. There are procedures in place and across all data centers for dealing with AC and DC environments and how you maintain them. But the IST question is probably the biggest one, because at the moment for AC, you use your heater banks, your standard heater banks that you get from any hire equipment from any hire company. And you just run them off your electrical infrastructure, and your cooling infrastructure cools the space, and you do that through your level 4s and your level 5s. The big challenge would be on a DC system, or certainly in an infrastructure if it's at DC, is how do you simulate the load? Now at the moment, to get a DC load bank, in the tens of kilowatts, they're scientific units, and they can cost tens of thousands of dollars, which is not really that feasible. But we if you have a think about it, realistically, if you just take a standard AC heater, you can keep the same elements. They'll still work on DC, but they'll just burn hotter. And change your AC motor for a DC motor, and change the AC circuitry for a DC power distribution board. You could theoretically come up with a DC load bank reasonably easily, but it would all be new. Certainly to do it on the scale of, say, some of what the hyperscalers would be doing. You're talking from between 2 to 6 megawatts in one go.
One thing I would like to mention is fault current, because Sean made a very good point with 18,000 amps of fault current that may happen with a conventional breaker. With solid state breaker technology, that would be reduced significantly should the fault occur beyond the breaker in the distribution segment. And the purpose is, the reason is because the reactive speed is much higher, and therefore you can actually preset the breaker to quickly turn off at any value given. So any other questions, please?
Yeah,
I am
there's
not able.
couple more. There's a couple more there now. Khalid has asked, what about the cooling restriction? And is there any safety concern related to the 1000-volt DC? And what is the purpose of the 200 kilowatt capacitor array ahead of each rack? And also,
Okay.
is the solid state breaker available in the market? I might do the solid state breaker one real quick. There are a couple of solid state breakers available at the moment at that amperage, at a high amperage. But realistically, the atom power one that Gabby has mentioned is one, and ABB sort of curbed the market a little bit in terms of their DC offering, and a lot of it comes from the marine industry. But it's compact stuff. The only thing I'd say is that they are very expensive, and there is limited supply. So we'll go from there.
Well, absolutely. And just one quick mention is that all the power distribution that we're utilizing today in the world is as a result, as in the beginning of the previous century, industry was rotating machinery. So pretty much all the AC power distribution has been designed, evolved into systems that were catering to rotating machinery. Now that all is changing. We need to look at new ways for the future. 50 years from now, the data center will totally look differently. Look at aircraft today, the Airbus A320neo using full solid state breaker technology for all of the secondary power distribution systems, and pretty much all the advanced aircraft does the same thing nowadays. And Khalid, to answer your question about the 200 kilowatt capacitor or capacitor battery array bank is like this. Because to down convert from 1000 volts to 50 volts is quite a daunting task. And in order to do that, there are actually two known ways: using a classic bridge converter. And I'm showing quickly, this is interesting. It's not shown in the picture, but imagine a big transformer that you have to use in a bridge converter, or you could use flying capacitor multi-level buck converters. And even with flying capacitor multi-level buck converters, the volume will be significant. So think about this. What if you can charge? Think about duty cycle, 50-50. So I have, and to simplify the conversation rapidly, imagine this. If you have 20 batteries, okay? And you have them in series, and you charge them for 2 seconds in series, and then for the next 2 seconds, you discharge them in parallel. Now you've got the equation, the basics of the equation to down convert from 1000 volts DC to 50 volts DC. Now, the battery is just a simple explanation just for analogy purposes. However, if you can conceive that the energy, the power density in capacitors is really high in watt per kilogram in mass terms. And the energy density also in capacitors over the last 15 years has evolved considerably. It is quite feasible to think about using capacitor banks, series parallel connections, and take that concept of duty cycle. 50% of the time you charge, and then the other 50% of the time, this part of it discharges, and while the other one is charges. So that's the reason why this bank is 200 kilowatts, because the actual load is 100 kilowatts. So half of the time you discharge half of it, and half of the time you charge. I hope that answers your question. Are there any other questions? I think we do have only 5 minutes left. So we're open here, and we're hot as we're going.
I don't see any more on the chat line. The one that I want to throw out there, and the one that I don't know the answer to actually, is something we discussed yesterday, which was vibration in the switchgear.
Yeah, that's right.
So I've experience with high power AC equipment or AC switchgear on metal skids, which are then placed on concrete pads, and everyone is going skid build, or deciding to go away from stick build. And one thing that I experienced was when the load was applied, or when the load was at 100% load, when the equipment was, at the time it was about 7.5 megawatts. The noise in the switch room was unbelievable, purely from just from power, just from the actual power running through the switchgear. It had to do with sheeting on the switchgear and all that kind of stuff. But it was the switch. Everything was perfectly safe. It was fine. But it was just the sheer noise due to the amount of steel work involved. And I'd be interested to know what would be the arrangement if it was at DC, because you don't have, you know, the power at modulating at frequency. You know, does it suffer from the same thing? Is it you know, because this switchgear was like, you know, 85, 90 dB at one. It was pretty loud. So
That's insane.
So I'd be interested if there's anyone out there who would know that, because that would be a significant improvement as well if we were to go that way.
Yeah, well, obviously, my only comment on this, Sean, it's everything resonates, and when we have a huge switchgear that's basically transferring the same power at the same frequency, things will start resonating, and as they resonate, they amplify exponentially nearly. So that makes sense for AC to require additional consideration on vibration. In the aerospace, there are specifications that pretty much everything gets tested in vibration up to 20,000 hertz in sine and random sine waves, and the equipment gets to be qualified according to these parameters following their testing. But as we all know, with DC, this problematic disappears. Obviously, it will still be present on the AC part where the transformers are housed into metal enclosures, but hopefully taken out of the insertion, like the transmission line, so many steps of AC will result in lower amounts of resonance into the equipment.
Excellent.
Okay. Are there any other questions? We do have 2 more minutes, and actually, if there are no other questions, I'd like to say thank you to OCP for allowing us to have this discussion. We encourage everybody to reach out again, and maybe questions come later, but remember, we are responsible for the future, and the data center of the future will probably hold some of the elements that we're discussing here today or tomorrow or yesterday. But the idea is that we all contribute for the better to better our world. So thank you all, and enjoy the rest of the day.
Yes, thank you very much, everybody.
Thanks, everyone.
Thank you so much to Gabby, Sean, and team. With that, we'll move on over to the next talk, which is also by Gabby. Gabby, thank you so much for staying on. We're seeing a lot of you this morning. Gabby is giving a talk on data center metrics efficiency. Is it PUE or efficiency? Gabby, I think you're still available to share. I'll hand the reins over.
And I am going